Welcome to the second lecture of this series. In this video, we are going to discuss the determinacy and stability of structures. Please listen very carefully to understand the concept. You might get confused if you refer to multiple books, so I would suggest sticking to one reference, or you can simply watch this video with full concentration. First, I'll classify whether a structure is stable or unstable, and then only we will move on to determinacy. First, let's study the types of instability. The first type is internal instability. So, what is internal instability? A structure is said to be internally unstable if it can't retain its shape when external supports are removed and a small disturbance is applied. For example, consider a structure which is supported by a hinge on one end and a roller on another end. And let's assume like there is a pinned or hinged connection in between. So let's consider the support is removed and a small disturbance is applied from this end. So it is gonna bend like this, which means it could not retain its original shape. Therefore, it is an internally unstable structure. Let's see a next example. A frame with hinge on one end and a roller on another end with a hinge in between. If the supports are removed, then our structure will be like this. And then if we apply some upward disturbance from the bottom, it is gonna rotate like this. So it could not retain its original shape. Therefore, it is internally unstable. On the other hand, if the structure doesn't change its shape when detached from the support, such structure are called internally stable structure. For example, a straight beam. It maintains its shape even if it is detached from the support. For example, a triangular structure without any hinge on the top. It retains its shape no matter what, if it is connected to the support or not. Another example will be a rigid frame. It won't change its shape even if it is detached from its support. For exam purposes, we usually don't need to worry about this type because in most problems there will always be supports and the question usually focus on other two type of stability or instability. Therefore, let's talk about second type of instability, which is external instability. A structure is said to be externally unstable if it has insufficient or improperly arranged support reaction to prevent the overall rigid body movement. Therefore, external instability of the structure is dependent on the number of the support and its arrangement. Now let's take a deeper dive into external instability. We will look into external instability for internally stable structures and external instability for internally unstable structures. For a plane internally stable structure to be in equilibrium, it must be supported by at least three reactions that satisfy three equations of the equilibrium. But if the structure is supported by fewer than three support reactions, the reactions are not sufficient to prevent all the possible movements. Such structures are referred to as statically unstable externally. So, when the number of the reaction is less than 3, such structure is statically unstable externally. One more thing, even if R is greater than or equal to 3, sometimes the structure may be unstable due to arrangement of the support. Such structures are called geometrically unstable externally. Now let's study a few examples of geometrically unstable structures. In the figure, a beam is supported by three roller support. And as we studied in the previous video that the reaction for roller support is perpendicular to the surface of the contact, which means for this support, the reaction is directed in this direction. For this roller support, the reaction is directed in this direction. And for this roller support, the reaction is directed in this direction. So all of the reactions line of action are concurrent at point O. Now if we take moment about O, summation of moment about O is equal to P multiplied by X.
P is the external force and x is the distance between line of the action of force P and the point of consideration, which is point O for our case. Now, as I said before, for a structure to be in equilibrium, we should have summation of force in x direction must be equal to 0, summation of force in y direction must be equal to 0, and summation of moment in z direction must be equal to 0. Clearly, our moment equilibrium is not satisfied. So here, the structure will rotate about point O. Therefore, this structure is geometrically unstable structure. Now let's move into next example. Let's consider a beam which is supported by a roller on this direction and a hinge on this direction. As discussed earlier, a hinge will have reaction perpendicular in the vertical direction and in a horizontal direction also. Similarly, a roller will have a reaction perpendicular to the surface of the contact. Let's say a external force P is being applied at a distance of x from this end. Let this point be O. We can see in the figure that the line of the action of all three reactions is concurrent at point O. So summation of moment at point O, it will be P multiplied by X, because we know moment is the product of the force and perpendicular distance between line of the action of the force and point under consideration. So clearly for this structure also, the moment equilibrium equation is not satisfied and it will rotate about point O. Thus, this is a geometrically unstable structure. Let's look into next example. A beam which is supported by three rollers. One roller at the end, one roller in the mid, and one roller at the end. Now let us consider a force P is applied in an inclined direction. Then we know that for roller, we'll have reaction perpendicular to the point of the contact. So we'll have one reaction on this direction for first roller, this direction for second roller, and this direction for third roller. So for this case, we have parallel reactions in the vertical direction, which means they cannot prevent the translation in the horizontal direction. For this case, if the angle is theta, then the horizontal component of the force P will be P cos theta and vertical component will be P sin theta. So if we apply the equation of the equilibrium here, summation of force in horizontal direction is equal to P cos theta, which clearly is not equal to 0. Therefore, the structure is geometrically unstable. Now let's look into external instability for internally unstable structure. For proper explanation, I have drawn a figure on the screen. It is a structure which contains two rigid members, AB and BC, connected by a hinge at point B. At point A, we have roller support, and at point C, we have a hinge support. Now, if you guys remember, this structure is an internally unstable structure. Remember why? It is because if we remove the supports, then if we apply a little disturbance from this end or this end, then it won't retain its shape. Therefore, it is an internally unstable structure. Now the question is whether the structure is externally stable or unstable. For answering that question, let's first write the number of the reaction. For roller support at point A, we will have one reaction in vertical direction. For hinge support at C, we will have two reactions, one in vertical direction and another one in horizontal direction. So in total, we will have three reactions. So total number of the reaction is equal to 3. Now if we apply some force at this location, there will be a overall rigid body moment because roller support it cannot provide horizontal support reaction and the hinge at point B it allows the rotation. Therefore our structure will be displaced like this. Since there was a overall rigid body moment, the structure is externally unstable.
But how can we make this structure externally stable? We can do that by changing the roller support with a hinge. So even if we apply force on this direction, the horizontal reaction from this support, it will prevent the translation on the horizontal direction. So we have total four reactions. R is equal to 4 to make the structure externally stable. Let's move into a new example. We have a member AB and BC connected by an internal roller. There is a fixed support at point A and roller support at point C. So let's identify the number of the reaction first. A fixed support will have three reactions, one in horizontal direction, one in vertical direction, and one will be a moment. And the roller support, it will have only one vertical reaction. So if we analyze the figure, then we can easily identify that member BC will have horizontal movement because both B and point C are supported on roller and they cannot resist the horizontal force. Therefore, this structure is externally unstable because there is again overall rigid body movement. So how can we make this externally stable structure? We can do that by replacing the roller with a hinge. So if we replace the roller with a hinge, then we will have a vertical reaction and a horizontal reaction, and the fixed will have horizontal reaction, vertical reaction, and a moment reaction. Therefore, the member BC is not free to move in the horizontal direction because of the horizontal support reaction at point C. Therefore, we have transformed the externally unstable structure to an externally stable structure by replacing a roller with a hinge, thereby preventing the overall rigid body movement. So that's all about stability and instability of the structure. Now we will move forward with determinacy and indeterminacy of the structure. As discussed earlier, the first step in solving this kind of problem is to classify whether a structure is stable or unstable. If it is unstable, then that's done. Your answer would be the structure is unstable and you don't need to go any further. But if it is stable, then you need to classify if a structure is determinate or indeterminate. So now let's begin with what a determinate structure is. So if we can find all the unknown forces using the equation of the equilibrium and the equation of the condition, then such structure are called determinate structure. So the unknown forces, they are either internal forces or the external forces. Internal unknowns are bending moment, shear force and axial force, and the external unknowns are the reaction. We have already known what equation of the equilibrium are, but I never introduced the concept of the equation of the condition, and I will talk about it a bit later. So for now, just keep in mind that if we can find the unknowns using the equation of the equilibrium and equation of the condition, then such structure are called determinate, or else they are indeterminate. If we cannot find the internal forces, then it is called internally indeterminate, and if we cannot find the external forces, it is called externally indeterminate. So total indeterminacy must be equal to external indeterminacy plus internal indeterminacy. Please remember this equation. We will be using this equation a lot to calculate the total indeterminacy, external indeterminacy, and internal indeterminacy of beams, frames, and truss. Before moving into that topic, I would like to explain about the equation of the condition, and for explaining that, let me scroll up to a image which I drew earlier. In this diagram, member AB and member BC are connected at joint B by a hinge. As discussed earlier, hinge cannot transfer the moment. Therefore, summation of moment at B in member AB must be equal to 0, and summation of moment at B in member BC must be equal to 0. They are the equation of the condition. But we might get confused that we have now 5 equations in total. But that's not the case because
above equation, they are not independent. It means if summation of moment at B in member BC is equal to 0 is satisfied with summation of moment is equal to 0 for the whole structure, then this equation is automatically satisfied. Therefore, number of the equation of the condition for this structure it is just 1 and we have 4 equation in total. Now let's study another example of equation of condition. I have redrawn a structure which we have studied already for the clarity. In this figure, member AB and member BC are connected by an internal ruler at point P. We have a fixed support at A and a hinge support at C. As stated earlier, hinge can't transmit force in x direction and it can't transmit the moment also. Therefore, summation of force in x direction of AB must be equal to 0 to be in equilibrium, and summation of force in x direction of BC must be equal to 0. Also, summation of moment at B for the member AB must be equal to 0 and summation of moment at B for member BC must be equal to 0. And as discussed earlier, these are just two independent equations, not four, because if this equation is satisfied with summation of force in x direction is equal to 0 for the whole structure, this equation is going to be satisfied automatically. And if this equation is going to be satisfied with summation of moment of the whole structure is equal to 0, then this equation is going to be satisfied automatically. Therefore, we will have just two equations of the condition. Thus, for an internal hinge, we have only one equation of the condition. For internal roller, we will have two equations of the condition. And in general, for hinge, equation of the condition is equal to n minus 1, where n is number of members meeting at a hinge. For example, if this is a structure and if this is a hinge, then equation of condition for this structure is equal to 4 minus 1 because 1, 2, 3, 4 members are meeting at this point. Therefore, we just have three equations of the condition for this figure. Keep that in mind.
Now, since we have studied about the equation of the condition, number of the equilibrium equation, known forces and unknown forces in a structure, we must be ready to move forward for the calculation of the determinacy and indeterminacy. First, let's begin with calculation of determinacy or indeterminacy in a frame structure. A frame structure will be determinate if we can determine all the unknowns using the equation of the equilibrium and equation of the condition. The unknowns are internal and external as discussed earlier. Internal unknowns in a frame structure are axial force, shear force and bending moment, while the external unknowns are reaction. And when will a structure be indeterminate? If we can't determine the unknowns using the equation of the equilibrium and equation of the condition, then the structure will be indeterminate. So, if we have more unknowns than the available equations, such structure will be indeterminate. Please keep that in mind. And what will happen if number of the unknowns is less than the available equations? Of course, the structure will be unstable. Now let us derive some equations for above mentioned condition. For doing that, let us consider a frame ABCD where there is a fixed support at joint A, there is a fixed support at joint D, C is a hinged joint, and B is a rigid joint. Then, for the equilibrium of the whole frame, each of its joint must be in equilibrium. So if we isolate the joint and recall that for the equilibrium of the each joint, they must satisfy three equations of the equilibrium, namely summation of force in x direction is equal to 0, summation of force in y direction equal to 0, and summation of moment about z axis must be equal to 0. Therefore, we will have 1, 2, 3, 4 multiplied by 3 equation of equilibrium. 4 multiplied by 3 equation of the equilibrium. And Since there is a hinge at joint C, it will provide equation of the condition. Since two members are connected at joint C, the number of the equation of the condition will be 1. So we will have one more equation of the condition. In this way, there are total 13 available equations to calculate the unknowns. And what are the unknowns? As discussed earlier, the unknowns are the reactions and the member forces. So how many reactions are there? One vertical reaction at A, horizontal reaction at A, moment at A. Vertical reaction at D, horizontal reaction at D, and moment at D. So we have 6 reactions in total. And there are 1, 2, 3 members. And if you recall, how many unknowns are there in a member in a frame? 3 unknowns, namely axial force, shear force, and bending moment. So how many unknowns are there? 3 multiplied by 3, because one member will have 3 unknowns, 3 member will have 3 multiplied by 3 unknowns. So in total, there is 3 3s are 9 plus 6 is equal to 15 unknowns. And how many equations are there? 13 equations. So number of the unknown is greater than number of the equation. Therefore, the structure is statically indeterminate. And the question also asks us to calculate the degree of the indeterminacy, which is the total number of the additional equation required to make the structure determinate. So it can be calculated by subtracting unknown minus the number of the known equations. So degree of static indeterminacy I is equal to total number of the unknown forces minus number of available equations. So in this case, it will be 15 minus 13 is equal to 2. Therefore, degree of static indeterminacy for the given figure is 2. Now let's generalize our formula. So in this equation, 4 was the number of the joint. If there are j number of joint in the structure, then we can replace this by j. This one is equation of the condition. Let's denote it by EC. So total number of the available equations, they are 3j plus EC. Therefore, total available equation 3j plus EC. And in this equation, 6 was the total number of the reaction. So in general, let's denote it by R. And this 3, it was number of the member. If a structure has m members, let's denote it by m. So total unknowns is equal to 3m plus r, and hence degree of static indeterminacy is equal to unknown forces minus available equations, which will be equal to 3m plus r minus 3j plus ec. So from now onwards, we can use this formula to calculate degree of the static indeterminacy. As stated earlier, if this number is less than 0, our structure will be unstable. If this number is equal to 0, our structure is gonna be determinate. And if this number is greater than 0, our structure is gonna be indeterminate. So if this number is greater than 0, structure is gonna be indeterminate. If this number is equal to 0, then our structure is gonna be determinate. And if this number is less than 0, then our structure is gonna be unstable. So this was the total indeterminacy. We can also calculate just the external indeterminacy and just the internal indeterminacy. Now for external indeterminacy, it will be also total unknowns minus number of available equations. So if we are talking about external, then the unknowns will be just external reactions. Therefore, total unknowns, they are reactions minus number of the available equation. If we are taking a structure as a whole, then number of the available equations will be 3 plus equation of conditions only because we are just looking for the structure as a whole. So if you are seeing the bigger picture, we will have just three equation of the equilibrium, and if there are any hinges or internal roller, then we will have equation of the condition. So that will be external indeterminacy. And internal indeterminacy, it can be calculated as 3 multiplied by number of the closed loop. So for example, if this is a structure, then in this case there is one closed loop, and for this structure there are two closed loops. So for this structure, internal indeterminacy will be equal to 3. For this structure, internal indeterminacy is equal to 3 multiplied by 2, which is equal to 6. We can also calculate it from the general formula. As stated earlier, total indeterminacy is equal to external indeterminacy plus internal indeterminacy, or internal indeterminacy is equal to total indeterminacy minus external indeterminacy. We can use the formula whichever is convenient for us. Please note that even if above formulas were derived for a frame structures, they can also be applied to a beam structures. And for beam structures, internal indeterminacy is always going to be 0 because for a beam there is never a closed loop. Therefore, total indeterminacy for the beam structure is always equal to its external indeterminacy. Now, let's see few examples for the calculation of determinacy or indeterminacy for a frame structure. So all you got to do is determine the variables in the equations. What is our equation? Degree of the indeterminacy is equal to 3m plus r minus 3j plus equation of the condition. Now all we got to do is plug in the value of m, r, j and ec in the equation. Now we might get confused to calculate the proper number of the member and proper number of the joint because of the presence of the hinge. Don't worry, I will explain about that also. If you consider a hinge is not dividing a member, then don't count it as a joint. And I believe that's a proper way to do it. But if you consider a hinge is dividing a member, then it must be counted as a joint. From either approach, you will come to the same answer. So, for the first case, if you consider the hinge is not dividing a member, then total number of the member for this figure is equal to 1, 2, and 3. So, number of the member will be equal to 3. How many reactions are there? 3 reactions for the fixed support and 1 reaction for the roller support. So number of the reaction is equal to 3 plus 1, which is equal to 4. How many joints are there? Remember, we are doing by the first approach where we are considering hinge is not dividing a member. Therefore, it should not be counted as a joint. So how many joints are there? 1, 2, 3, and 4. And what is the value of the EC for this figure? EC will be equal to number of the members connecting at a point minus 1, which is equal to 2 minus 1 equal to 1. So if we plug in these values, then we will get degree of the indeterminacy is equal to 3 multiplied by 3 plus 4 minus 3 multiplied by 4 plus 1. And if you solve, you will find I is equal to 0. Therefore, this structure is statically determinate. And if we try to solve it by another approach where we consider a hinge is dividing the member, then how many members are there? 1, 2, 3, 4. So in that case, number of the member will be 4. Reaction will be same and number of the joints, it will be 5 because 1, 2, 3. The hinge is dividing a member, so it should be considered as a joint for this approach. So number of the joint is equal to 5 and EC is equal to 1. So degree of the indeterminacy is equal to 3 multiplied by 4 plus 4 minus 3 multiplied by 5 plus 1. This value is equal to 16 minus 16 is equal to 0. So again we came to the same conclusion. The structure is statically determinate. Now if you want to verify your answers, we can do that by drawing the free body diagrams. And for drawing a free body diagram, all you need to do is separate the structure from the support and add the hinges. So if we separate this structure, add the support and add the hinge, then it is going to look like this. So this joint, it should be subjected to three support reaction, right? So I will write those reaction over here. One in vertical direction, one in horizontal direction, and one will be a moment reaction. This part, it will be just subjected to a vertical reaction from the support. And what will happen at this two part? We will have a horizontal force, axial force, and a vertical force, shear force. Remember, at the hinge, the moment is zero, so we are not going to write that moment over here. And for Newton's third law of the motion, we should have another force going in this direction to cancel this horizontal reaction. We should have a force going in that direction to balance this vertical reaction. So, how many unknowns are there? Total unknowns, I will denote this by R, is equal to 1, 2, 3, 4, 5. Don't count this as 6 and 7 because they both mean the same thing, right? So 1, 2, 3, 4, 5, 6. Total unknowns is equal to 6. And how many parts are there in this structure? One part and two part. We have three equation of the equilibrium for each part. So total equation is equal to 3 multiplied by 2 is equal to 6. Since we have unknowns equal to total number of the equations, this structure is statically determinate. Now I will show you one more method to calculate the degree of the indeterminacy for a frame structure, and the name of the method is open tree method. In this method, we are going to convert the given structure into a open tree-like structure. The open tree that we are considering for this purpose has a fixed support at its base and all of its joints are rigid. And as the name suggests, it does not have any closed loop. But of course, our structure, they never look like an open tree. Therefore, we need to make some adjustment by doing some cuts and adding some additional restraints. Let's make an open tree structure for this problem that we have solved already. So for making this structure as an open tree, I need to make a cut at this portion. Doing that, the structure is gonna look like this. Now you need to check if it looks like an open tree or not. As I told earlier, for a structure to look like an open tree, it needs to have a fixed base and all of its joints must be rigid. So considering this left part, we have a fixed base, it's perfect. But here there is one hinge. And how can we make it rigid? By providing a moment resistant over there. So we will need one restraint at this location. And looking at the right part, is there a fixed base at support? Nope. So how many restraints are required to make it a fixed base? Two, one in horizontal direction and one will be a moment resistant. Therefore, we will need two more restraint in this part to make it as a fixed base. And check for the joints. Are all the joints rigid? Yes, they are rigid. Now your formula for the calculation of indeterminacy is degree of the indeterminacy is equal to 3 times number of the cut minus number of the additional restraint required to make the bases fixed and the joints rigid. So for our case, it will be equal to 3 multiplied by 1 because we just made only one cut minus what were the number of the additional restraint? 2 plus 1 is equal to 3. So degree of indeterminacy is equal to 0, which is the value we previously got for this structure. So that's all about open tree structure. Let's move into next example. So I will start first by using the method of the equation. Remember the formula. The degree of the indeterminacy, it is equal to 3 times m plus number of the reactions minus 3 times number of the joints plus equation of the condition. So for this structure, number of the members is equal to 1, 2, 3, 4, 5. I am not considering the hinge is dividing a member. Therefore, number of the member for this structure is 5 plus number of the reaction will be 3 for this fixed support, 3 for this fixed support, 2 for this hinge support, and 1 for this roller support. So in total there is 9 reactions minus 3 multiplied by what's the number of the joint? 1, 2, 3, 4, 5, 6. Remember, since I did not consider the hinge is dividing a member, I am not counting it as a joint. Therefore, total number of the joint is 1, 2, 3, 4, 5, 6. 6 plus. So what's the equation of the condition? For this one, we will have one equation of the condition, and for this hinge, we will have one equation of the condition. If you get confused, then formula for equation of the condition is equal to number of the member connecting at a point minus 1. So in total there are two equations of the condition. If you solve this, you will get 4. Therefore, the degree of the indeterminacy for this structure is 4. Now, you might also want to calculate either that is external indeterminacy or internal indeterminacy or sum of both. For internal indeterminacy, as I told you earlier, it will be equal to 3 times number of the closed loop, 3 times number of the closed loop. So are there any closed loop over here? No. Therefore, internal indeterminacy is equal to 0. And what will be the external indeterminacy? It will be equal to number of the unknowns minus number of the available equations. So what was the total number of the reactions? 3 plus 3 plus 2 plus 1, which is 9, minus 3 plus what was the total value of EC? 1 plus 1, which is equal to 2. 9 minus 5 is equal to 4. So the external indeterminacy of the given structure is 4. And we can verify our answer again by the formula. Total indeterminacy is equal to external indeterminacy plus internal indeterminacy, which is equal to 4 plus 0 is equal to 4. The number is same as we calculated earlier. So let's solve the same problem by drawing the free body diagram, and as discussed earlier, in order to draw the free body diagram, we need to separate the structure from its support and at the hinge locations. So our structure is gonna look like this after separating from the support and hinge. After removing it from the supports, we need to replace it by the reactions, and at the hinge location, we need to replace it by the internal forces. So at this location, there was a hinge support, therefore it will have vertical reaction and horizontal reaction. At this location, there was a fixed support, therefore we will have vertical reaction, horizontal reaction, and moment reaction. Similarly, at this location, we will have vertical reaction, horizontal reaction, and a moment reaction. At this location, there was a roller support, therefore we will have only vertical reactions. And for the hinge, we will have shear force and axial force. If this is directed on this direction, we will have another force on its opposite direction, and if we have one force in vertical direction, we will have another force in the opposite direction. Similarly, we will have the similar situation on this side also. Now count the total number of the unknowns. The total number of the unknowns are 3 plus 3 plus 2 plus 1 plus 2 plus 2. Remember I said plus 2, not 4, because if one of the forces are known, then another force will be just opposite of that. It is just a pair of the force from the Newton's third law. Therefore, total unknowns are 13. And how many parts we got? The number of the parts is equal to 1 part, 2 part, three part. And for each part, we will have three equation of the equilibrium. Therefore, for three part, we will have 3 multiplied by 3 is equal to 9 equation of the equilibrium. Therefore, degree of the indeterminacy is equal to unknown reactions minus number of the equilibrium equation, which is again equal to 4. Now let's solve the same problem by open tree method. For doing that, we need to make cuts to the structure to make it look like a open tree. So I will make one cut over here, one cut over here, and one cut over here. And then I'll just check if the bases are fixed or not. We have a fixed base, we have a fixed base. Here we will need one more reaction to make it a fixed support. Here we will need one more reaction to make it a fixed support. And for the hinge, we will again need one restraint to make it a rigid joint, and here also we will need one more restraint to make it a rigid joint. Therefore, the degree of the indeterminacy is equal to 3 times number of the cut minus number of the additional restraints required to make it look like a open tree. So that will be 3 multiplied by what was the number of the cut? 3 minus what was the number of the additional restraint? Sorry, this should be 2. So 1 plus 1 plus 1 plus 2, which is equal to 5. Again, the value is 9 minus 5 is equal to 4. So we came to the same conclusion by all the three approaches. Now let's take a look into next example. First, we will try to solve it by the method of the equations. So here, the total number of the member is equal to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And total number of the reactions 3 for the fixed support, 2 for the hinge support, 3 for the fixed support. That will be 8. Total number of the joints 1, 2, 3, 4, 5, 6, 7, 8, 9. Total number of the joint will be 9. And what will be the value of EC? As discussed earlier, it will be number of the member meeting at a point minus 1. For this case, there are 1, 2, 3, 4 member meeting at a point. Therefore, value of EC will be equal to 4 minus 1, which is equal to 3. Now, if we plug in the value in the equations, then we will get 3 multiplied by 10 plus 8 minus 3 multiplied by 9 plus 3, which will be equal to 38 minus 30. This value is equal to 8. And we can also calculate this value by calculating the external indeterminacy and internal indeterminacy and summing up the values. So the external indeterminacy is equal to R minus 3 plus number of the equation of the condition. So for this case, R is equal to 8 minus 3 plus 3, which is equal to 2, and internal indeterminacy is equal to 3 multiplied by how many closed loops are here? This is one closed loop and this is another closed loop. Therefore, there are two closed loops. So this value will be equal to 3 multiplied by 2 is equal to 6. Therefore, total indeterminacy is equal to external plus internal, and 2 plus 6, which is equal to 8. Therefore, we got the same value. Now let's solve the problem by method of the open tree. As discussed earlier, an open tree needs to have a fixed base, rigid joints, and no closed loops. So, for changing this structure into an open tree, I need to make a cut right over here, another cut at this location, another at this location, and finally another cut at this location. So for clarity, I will just separate these parts. Now if you look at the left part, then does it look like an open tree? Yes, it does, because it has a fixed base. It does not have any closed loop and all of its joints are rigid. Similarly, on the right part, it is also an open tree already. We don't need to do anything over here. But for the central part, there is a hinge over here and we need to add restraints. And how many additional restraints we need? It will be equal to equation of the condition, which is equal to EC is equal to number of member meeting at a point minus 1. For this case, 1, 2, 3, 4 members are meeting at a point. Therefore, the value will be 4 minus 1, which is equal to 3. And does this have a fixed base? Nope. What do we need to do to make this hinge support to a fixed base? We need to add one moment restraint. Therefore, we will need one more restraint at this location. So total that will be equal to 3 plus 1, which is equal to 4. So for this case, the number of the additional restraint R dash is equal to 4. How many cards did we make? 1, 2, 3, 4. Therefore, C dash will be equal to 4. So the formula is a degree of static indeterminacy is equal to 3 times number of the cut minus number of the additional restraint. So if we plug in the value, we will get 3 multiplied by 4 minus 4, which is equal to 12 minus 4, and the value is again 8. So we got the same value by the method of the open tree also. Now let's try to solve the same structure by drawing free body diagram. And as we learned earlier, in order to draw the free body diagram for determining the indeterminacy, we need to separate the structure from the support and from any hinges which is present in the structure. But for a frame structure which has a closed loop, we need to use the method of the sections and cut the loop apart. Now let's draw the free body diagram for the structure. And as stated earlier, we need to separate the structure from the support at the hinge location, and we need to make section cuts if the structure has closed loop. So the left part is gonna look like this. The support must be replaced by support reaction. We will have one vertical, one horizontal, and one moment reaction. At this point, we will have internal forces, axial force, shear force, and bending moment. And at this location also, we will have axial force, shear force, and bending moment. Similarly, on the left part, we will have the same situation over there also. And the tricky part is middle portion where we need to separate the structure from the internal hinge also. So I'll separate it like this. And at this location, we need to replace the support by the support reactions. And since the hinge cannot transfer the moment, we should have a zero moment at all of these 4 points. So they will just have shear force and axial force. I am not worried about the direction of the arrows because they are just used to represent that the force exists in that part, but they might not represent the correct direction. Similarly, on the end point also, we will have the external force. But on this part, I am concerned about the arrow direction. They must be drawn opposite to this side. And here also, they must be drawn opposite to the forces on its side. Now the formula to calculate the degree of the indeterminacy is degree of the static indeterminacy is equal to R minus 3n. Now the tricky part is to calculate the value of R. The calculation of the support reaction is straightforward. We just have 3 plus 3 plus 2 is equal to 8 support reaction. I'm sorry, we need to show the force on this part also on opposite direction to the adjacent one, and then we need to calculate the remaining unknown also. So if you remember, these are just three unique unknowns because if one of the pair is known, another pair will just have an opposite value of it. So this is three unique unknowns, three unique unknowns, three unique unknowns, three unique unknowns. So 12 unique unknowns. And this part is a bit tricky. How many unique unknowns are here? There are 6 unique unknowns here because if we know three forces on the horizontal direction and three forces on the vertical direction, then the force on the horizontal direction and vertical direction of this member can be known. Therefore, here are 6 unique unknowns. So the value will be 6. Therefore, total R is equal to 26. How many number of the parts over here? One, 2, 3, 4, 5, and 6. So the value is again 8. In this way, we can verify our answer by using multiple approach. Alright, this video is getting a bit long, so let's wrap it up here. Today we learned how to calculate the static indeterminacy of beam and frame structures using the method of the equations, free body diagrams, and open tree method. I hope you found this explanation helpful. If you did, please don't forget to like, share, and subscribe to support the channel. In the next video, we will continue with static indeterminacy, focusing on the truss structure. See you there.